Our next speakers are Dimitri Tymoczko, has written a very famous book about chords and geometry. He's in Princeton University. And then we have Jason Yust, who is at Boston University, who has worked on Fourier transform mainly. I'm giving you.
So we are not. We need some help with the
Sure.
video.
Absolutely.
It looks better when it's at the normal resolution. And let me just load up a few more things here. And so this was very mysterious because we were starting in very different places, but coming to the same result. And one thing I will say is if you are interested in today's topic, there's a website where you can explore some of these ideas, and the website is listed here, and it will show up again. So with that late start, we are now ready to go. And okay, so what we'll be talking about is Fourier phase and pitch class sum. Fourier analysis here used in the context of set theory rather than audio processing. And what we're going to say is there's a fundamental convergence between two very different music theoretical worlds, voice leading space and Fourier space. This convergence only appears in delicate circumstances. For points or chords, typically when we limit ourselves to the transpositions of some particular chord lying in some particular scale, and for voice leadings, only when the chord divides the octave evenly or nearly even. And to explain this correspondence, we need to think rigorously about how to represent voice leading in the context of Fourier analysis. And here there are two separate routes to go down, one which we call glide paths versus crossfade paths. So one interesting result of the work we've done is just to get clearer on what paths in the different Fourier spaces represent. So the first part of the talk involves circular voice leading space, which is a new and simplified representation of voice leading possibility that I've been working on over the last year and a half, and it avoids some of the complexities of the ideas in my book. You don't have to imagine 7 dimensions to think about 7 note scales. So we start with circular voice leading spaces. These are abstract and simplified representations of the higher dimensional configuration spaces representing n-note chords. In these spaces, points represent entire chords. The spaces represent the bijective, strongly crossing free voice leadings among the transpositions of any n-note chord in any d-note scale. If that doesn't mean anything to you, you have to read my book because we can't explain it now. The diagrams look like a spiral that winds n times around an annulus, that's a punctured disc, with d chords spaced equally along it. And if you want to play with them, the website is here. So here is what the spiral diagram looks like for chromatic triads. So triads in the 12-tone equal tempered chromatic scale. You see C major. The point C represents the C major chord. E is E major. G sharp is G major. And those lines divide the circle into 12 equal slices. You'll see the circle winds around. There's a spiral that winds 3 times for 3 notes in the chord. And then chords are evenly placed. There are 12 chords evenly placed along the spiral. Over here on the right is the diagram for 7-note chords in a 12-note scale. Here the line winds 7 times around the spiral, and again, we have 12 equally spaced points along it. And the best way to learn about these, oh yeah, that sometimes happens. That's just bad things happen. Okay, so you can go to my website, you can put in any chord and any scale, and you can click on a point, and so that point represents C major. And then as you move along the spiral, all voices are transposed down chromatically. And a complete circle in the space. So moving along the spiral represents transposition along the scale. And moving in a complete circle, starting and ending at the same point, represents what I call transposition along the chord. Okay, so each note goes up one chordal step. And the cool thing is you can put in any old chord you want, come up with the spiral diagram, and this gives you a very simple and easy to use representation of voice leading possibilities, which I developed mainly for the use of my students, but is actually quite a cool compositional tool for exploring voice leading in any scale with any chord. Now, the thing that's interesting about all of these spaces is because the way they're set up, the sum of the pitch classes in a chord corresponds to its angular position. So if you have multiple chords at the same angular position, they have the same pitch class sum. And what we're going to see is a very similar construction arises out of the Fourier perspective. So there's basically three rules for interpreting motion in the space. Moving along the line represents transposition along the scale. Angular position therefore represents pitch class sum. A complete circle is transposition along the chord. And then homotopic paths represent the same voice leading. So there's a natural notion of composing paths. Now I'm going to turn it over to Jason for Fourier space.
So I'll do a little introduction to the Fourier space. And there's a couple ways we can think about this. I'm going to do a very quick introduction. Hopefully some of you have encountered this work before. One way to think about what we're doing the Fourier decomposition of some kind of pitch class set here, a C major triad, is we can think about we're extracting periodic components from that. So each of the components is some period dividing the octave into any number up to 12 parts, but if you get above 6, then you simply have the complex conjugate, so we can basically ignore those. But for the purposes of this paper, we can think of these rather in a complex space. And here we see that the reduced octave that is an emergent feature of the voice leading approach is kind of a feature that's defined into the Fourier approach, which is where a lot of these correspondences come from. So the Fourier approach is looking at periodic components. We take, say, the periodic component that divides the octave into 3 parts. Then what we're dealing with is essentially in a space that's based on a reduced octave that divides the octave into 3 parts. And the way we can get these components in complex space is simply to sum unit vectors where a unit vector, each pitch class corresponds to a unit vector, right? So if we were, say, we wanted to find the third component of a C major triad in a complex space, we take the unit vectors for C, E, and G, and we sum those as vectors, and we get a vector that has both a magnitude and an angle in the space. We're mostly interested here in the angle in the space, which is what we call the phase. So we're looking at the resulting phase of this vector sum, and that is, what we'll be considering in this paper only the case where the index of the component is equal to the size of the chord. This is where we get these correspondences of the index of the component the component is very large when the chord divides the octave relatively evenly. So this is the phase. We can use the Greek letter for in radians. We'll mostly divide the octave into 12 parts, which means, so I'll use a pH symbol for that. So here's 2 examples. We can think about, say, 3-note chords. We have major triads. Here's how they arrange themselves in this space. So here's just as complex values for the third component. You see that the major third related triads end up in the same place, and they arrange themselves around the circle with ascending semitones going in this direction. We can also do the same thing with, say, 5-note chords. For the 5th component, here I arbitrarily chose minor 9th chords, and they will arrange themselves in the complex space so that the phases that moves 1/12 of the complete circle for each fifth. So you can see how these, we get this first correspondence, and it's important to recognize this only works if we're dealing with one chord type, one transposition type. But we get a very strong relationship in that case. If we're dealing with one transposition type, we can say that if you look at the pitch class sums, so the positions in the voice leading space that Dimitri was talking about, the difference of pitch class sums in that circular space will be exactly the same as the difference of the phases between the chords. Right? So we have an exact correspondence if we're dealing with one chord type. Now, if we're dealing with multiple chord types, so here's the example where you have here's the phase space, and here are the pitch class sums. The chords are in exactly the same positions in both spaces for major triads. And here again, if we have the minor ninth chords, here they are as pitch class sums in the voice leading representation. Here they are as phases in the Fourier representation. So they're exactly the same, but they don't actually. They're exactly the same, but rotated around. So here's the D minor ninth. Here's the D minor ninth. So the differences are the same. The arrangement around the circle. But if we're dealing with chords that are of different set classes or transposition types, this doesn't necessarily hold. So here we have two chords that have the same pitch class sum. Here, C major triad and C sharp E F sharp. So an no 2-5 chord. And those have there's a balanced voice leading from one to the other, so they fall in the same place in this space of pitch class sums. But they have completely different phases in the third component Fourier space. So if we're comparing different chord types, then we don't get this nice correspondence, but there's still more we can say. And I think that takes us over to the next.
Okay, so if we just think about the positions of points in these two representations, and we limit ourselves to the transpositions of some chord and some scale, they look very similar. The next question is about voice leading, or the mappings from one point to another, paths from one point to another. Okay, so to think about that correspondence, we have to think about the prior question of how you represent voice leading in the Fourier representations. In the configuration spaces, in the voice leading spaces I usually work with, voice leadings are typically represented by paths. These are the paths that would be taken if each pitch class glides smoothly from its starting point to its destination at a constant velocity, starting and stopping at the same time. Actually, any homotopic path will deliver the same voice leading, but I call these are the sort of basic ones that I call generalized line segments. In my book, they are the images of line segments in the covering space. So, how do we represent voice leading in Fourier space? And here I think Jason has been working with concepts of voice leading, but one of the advantages of our paper is we finally got together and really worked out the details. Basically, there are these, there are two strategies. One strategy we call glide paths. And here we just do the same thing we do in voice leading space, but in Fourier space. So take the path where each note glides smoothly to its destination, and then just look at the Fourier transform of each point along the path. That produces a nice smooth path in Fourier space that can be taken to represent the voice lead. The second strategy, which is maybe the more typical one, we call crossfade paths. And here we simply interpolate linearly between the vectors corresponding to the first and destination chord. So those are two possible strategies, and now we're going to ask what is the relation between those paths in the Fourier spaces and the voice leading paths in the voice leading spaces.
Okay, so the first question we asked is just dealing with glide paths in Fourier space. We can make a nice simplification of this first question. The basic question is the voice leading space homotopic with the Fourier space, if we're considering just the phases of the Fourier components. And we can reduce that to a simpler question, and the details of that are in the paper if you want to investigate that. I won't go into that detail. But all we really need to ask then is, if we have a balanced voice leading, in other words, a voice leading where the motion sum to 0, can we ever have a balanced voice leading between two chords of the same type that where the phase motion is non-trivial. In other words, the phase motion makes some kind of loop in the space. The answer is, first of all, we have a good result where the chords are relatively even, and we can say the two spaces are essentially homotopic. In other words, if we have a voice leading between any two chords that are of a relatively even type, like a major triad, the phase motion in Fourier space will be homotopically equivalent. It will not loop the entire phase space. So a simple example is from two major triads that are major third related, C major to E major. This motion it'll move, the phase value will move a little bit, whereas the voice, the pitch class sum will not change at all over the course of the voice leading. But it will return to its original destination, so it's homotopically equivalent to a point. And we have a illustration of that, I think. So in this illustration, what we'll see is actually the glide path. So here in the gray are the pitch classes moving. The blue is the phase of the resulting phase. You can see that it actually stays almost exactly the same. I don't know if the phase really even moves.
It changes a little bit.
It changes a little bit. Okay, so why don't we just show the second example here while we're at it. So the next result is that if the we can have a balanced voice leading that's homotopically non-trivial in phase space if the chord is relatively uneven. This example you're looking at is an O2-4 triad going from C, D, E to G sharp, E, F sharp, right? So it's transposition by 4 plus a scalar transposition, so a change of the ordering of the voices. And what you get is the space tracks one of the voices, which makes a complete cycle. So it's actually easy to come up with these examples where we can have a balanced voice leading that's homotopically non-trivial. Let's go back to the third. And we go back to the slides now. Okay, so here's in voice leading space. Here's what we were just looking at. So that's what we just saw. So we have a relatively uneven chord. So the natural question here then becomes how even or how uneven. As we say, how uneven do we need to be to get this kind of phenomenon, right? And that's actually a harder question to answer than we initially thought it might be in investigating this. So we were able to come up with examples like this one. These don't happen in the 12-tone equal tempered scale, but we can come up with ones, say, in a third tone scale here, where you can see the voices in this example represented by those vectors actually there's a certain part of the phase space where those voices never cross through. So the phase doesn't exactly track exactly a single voice, and yet the phase still does make a complete circuit of the space, and this is a balanced voice leading. So we have the voice that's traveling the most is the one that's going from F sharp plus a third tone down to D. That one travels not a complete circuit, but a pretty, almost a complete circuit. Complete circuit is a major third, and this one goes by just over a minor third. So I guess we could attend to it.
So there is an interesting open problem here, which is to find precise bounds for this, when this correspondence works and when it doesn't work. We tried lots of hypotheses and did lots of investigations, and we found anomalous cases like this that sunk our various hypotheses. So if you want a medium hard problem, you're welcome to solve this for us.
We have a pretty easy bound, which is that I think they cover half the space, and then we know that we're okay. But that's easy. That's not very aggressive. To do this one too. Okay, right. So now thinking about crossfade paths, this is mostly the way that people, myself included, who talked about the Fourier transform on pitch class sets have thought about these, not in a universe where of a continuum of log frequency, like in voice leading spaces like these glide paths we're talking about, but instead being in a universe of pitch classes with various weightings. So we can say pitch class distributions are what's dealt with by cognitive scientists when they look at key profiles and so forth. So if we're in that universe, we can think about path from one point to another not being the continuous motion of voices, but of certain pitch classes fading out, so to speak, while others fade in. In other words, we're continuously moving the weightings of pitch classes to get from one to the other. We can construct a canonical path that we're calling a crossfade path from one chord to another that simply fades out the elements unique to one chord as it fades out the elements unique to chord B, right? And what that is essentially in the larger 12-dimensional Fourier space, it is just taking a direct line from one point to another within that space. So it's just the shortest distance from A to B. And it will also be the shortest distance in phase space for that reason. This means that if we're, I'm going to give some examples in the F5, in the fifth component space. This consequence will come out of that. I want to show the examples first, though. So I've described this space as a space in previous work as a space of keys. We can arrange the 12 diatonic scales in this space, and their positions will correspond to the number of accidentals in the key signature. So we have a similar phenomenon in voice leading space also. But we're thinking of the paths differently here. If we're thinking of a crossfade path, and as we're going from C major, say, to G major, what we're doing is not moving F up to F sharp. That would be the glide path. The crossfade path will fade out F as it fades in F sharp, right? So it has a similar result in terms of the points in the space that are connected, but we're conceptualizing it differently. So here the point between C major and G major is a scale that has a little bit of F in it, a little bit of F sharp, right? It has both of those in some proportion. As opposed to the glide path where we're talking about a 7-note scale still, and we're talking about a note that's halfway between F and F sharp is the midpoint between those two scales. So we're making that path. Now, if we take a more distant route in this space, the advantage of voice leading is that if we're simply directly connecting one point to another, we can think of it as moving in either direction along the cycle. So if we're going from C major, say, to D flat major, we can imagine doing that via a descending voice leading, where we have 5 notes that change from naturals to flats. Or we can think of it in terms of an ascending glide path. That's the lower arc there. This is in complex space where that circle in the middle is actually the unit vectors. So these are very far away from the center of the space. But you see the glide path in that space. If you're ascending, that corresponds to just taking every note and moving it up by step. And that will move you a different direction in the space. If we're thinking about the crossfade path, then we're directly connecting 2 points. And so that's simply a straight line in the space. And you can see there the point that's halfway between C major and D flat major is then something that includes all pitch classes with C and F at weight 1 and all the other pitch classes at weight 1/2, right? So that would be the midpoint, right? So it's a different conceptualization of that path, but also a different result. And here, if you, the main point here is that if you're thinking about crossfade paths, in order to connect 2 points in an inefficient route around the phase space, you have to include some intermediary point. Because the crossfade paths are defined simply as the shortest way from A to B, they'll always take the shortest route. So distinguishing between, say, an ascending voice leading and a descending one would require you to have some other intermediary between the two.
Okay, and just to explain why that's relevant, we have these 2 circles of fifths arising in these 2 contexts, 2 circles of fifth-related diatonic scales. One shows up in Fourier analysis, one shows up in the voice leading spaces. There's a question, which one is the representation, the best representation of phenomena like enharmonicism? In our paper, we show that we say that it's the voice leading space that tracks enharmonicism in many musical contexts. That opens to a deeper question of, are there other varieties of enharmonicism that don't involve scales at all, maybe arising out of just intonation? And that's another interesting question. Okay, we're just going to end the last part of our paper talks about the connections between Fourier, this Fourier approach and the voice-leading approach. A long time ago, I argued that Fourier magnitudes closely approximate the proximity to the nearest double subset of a perfectly even chord. So we can get some part of the results of Fourier analysis by translating its questions into voice-leading questions about essentially what the nearest perfectly even chords is. We can do something similar with Fourier phases. It turns out that the phase of a Fourier component can be associated pretty closely with the transposition of that nearest double subset of the nearest perfectly even chord. Here's some graphs that show the relationship between phase and the transposition of the nearest subset for trichords, tetrachords, and pentachords. These are like a million chords, and Jason had to, it was originally like a PDF with a million points in it that crashed our computers. So using these relationships, we can approximate many features of the Fourier perspective using voice-leading tools. What's interesting is that back in the early days of voice-leading and Fourier analysis, Ian Quinn had a kind of Platonist vision where these two tools were pointing at the same abstract reality. That turns out not to be true in general, but here we're kind of coming back to Quinn's vision of a sort of a pseudo-Platonist correspondence in some circumstances between these two very different approaches. The interesting question, I think, for future work is what features of Fourier analysis resist this translation into voice-leading terms? In other words, what is it giving you that's maybe more distinctively harmonic that you can't get out of a voice-leading analog, and we don't, we leave that for future work. And so thank you very much.
Okay, questions, comments? Please.
I'm very grateful for this research because you have just concluded it's getting back to Ian's original idea. Very nicely putting together these voice readings and Fourier analysis. As for the questions that remain open, I think maybe you have considered the different topologies of the spaces you are acting in. Because if I see it right, in the case of movements fading out of straight lines in Fourier space, when you only examine the faces, the angles, then you're moving on a torus. And actually, Jason mentioned this in passing, that you have so many straight lines from one point in phase space to one other point in infinity of straight lines, actually. And there are those questions that generalize in Schubert, different ways to go from, I think it was A flat to G flat. And by voice leading, you're moving to a different space, a more complicated one, logically speaking. And I think that you may have some good correspondences in the mostly even chords because you're in the center or the orbifolds where the topology is quite neat. And there locally you have diffeomorphisms between the two spaces, but globally you don't because the fundamental proofs are quite different. Have you tried to investigate this?
I mean, that's kind of what we've spent a lot of time looking at here, right? Is that when we're talking about the topology of just a single-dimensional phase space, we're talking about exactly that problem. You can connect things in opposite directions around that space. Yeah. So obviously, in my Schubert paper, I talk a lot about. I mean, we have this issue here of whether you can have a rational reason to go different directions in this diatonic space, if you will, in this seventh component or fifth component Fourier space. And in the Schubert article, I talk a lot about reasons why you might want to understand things going in different directions along that cycle. I think that's important to that particular harmonic language. And what that involves is thinking of different kinds of intermediaries that would cause you to go one direction or another. So to me, that there's an underlying musical reality to enharmonicism that isn't necessarily reflected in the kind of notational or scale-based formalization of it. So it can be very well formalized by means of accidentals on 7-note scales, by means of spelled heptachords, or however you want to put it, voice leading space, 7-note voice leading space. But to me, there's an underlying musical reality that doesn't necessarily require you always to be working in 7-note objects. That in fact, you can have intermediaries that involve a single pitch class that's a common tone between 2 scales, or a chord, a series of chords that you don't necessarily know what scale they're in, but you know that they make some kind of enharmonic cycle in a sharpward or a flatward direction, right? So that's the basic kind of conceptual, underlying conceptual distinction that we are working through in that.
If I can just give a very quick other answer about this. The first thing is that the topology of the voice leading spaces, if you ignore voice leadings that have voice crossings in them or voice exchanges, the topology is extremely simple. There's one circular dimension, and then there's a ball. And that's it. It's a ball times a circular dimension. These circular voice leading spaces show that circular dimension and compress the ball into a line, but you lose almost no useful musical information in that context. And so it doesn't matter whether the chord is even or uneven. It is this same graph and this same topology, and that's the beauty of the spaces and why they represent a step toward the topological perspective. But the topology of this graph is the topology of an annulus or punctured disk. There's no point in the center of the circle. Okay? Now, when we are talking about Fourier phase spaces and looking at just one Fourier component and its phase, the topology is actually of the plane, not of the punctured disk. So precisely that difference in topology causes problems because you can move between antipodal points here and here through this center, and in the voice leading space, you have to choose one of those 2 paths. So that difference topologically is very important, and we kind of try to, we have to avoid situations where that's one of the many factors that can break this analogy. Okay, we're out of time. Thank you very much.